Sometimes these Sunday morning sessions, I get a ton of people, and sometimes I get almost none. So it's all over the place. It depends on the class and how convenient it is, and so on and so forth. So I'll start with the issue that you brought up, and then I'm gonna go over kind of a survey, since I didn't get too many other questions, a survey of what would be likely to be on the test, what materials that we've gone through, kind of chronologically. So let's start with this issue of probability. So I'm going to take it from this point. Let's see. Okay. So if I can't get this to work. Uh-oh, my pen's not working here. Hang on just a second. Okay, unfortunately, my graphics pen is not working right now, so I kind of have to do this kind of with the mouse trackpad kind of deal. So let's talk about probability. One of the things that we reviewed was this idea of independent, whether a sample is independent and whether it's mutually exclusive. So when we talk about independent samples, we're talking about, for instance, the idea that well, if I randomly sample a population, say I'm concerned about what percentage of the population has diabetes. If I really truly randomly sample the population, well, in the first person I select, if the prevalence of the population in the population is 10%, the probability that that first person I select has diabetes is 10%. Now, since it's a large population, it's not just three. In other words, if it was three people, and we know, and the prevalence was 33%, we know if the first person we sample is has diabetes, we know the other two don't. So the only way to make that random is to have replacement, put that person back into the population, and he's part of the random sample again. But with a large population, that's usually not necessary. It doesn't affect it that much. So let's say we have a 10% prevalence in the population. I pick a random individual, and they may not have the probability they have diabetes is 10%. Then I go back and randomly pick someone again. It's the same probability. I haven't changed any of those conditions, right? The probability that I would find successive people that have diabetes when I randomly sample like that is going to be unaffected by the previous sample. So the probability, say that I would pick two people in a row that have diabetes is 10% times 10%, or it's 1%, right? 0.1 times 0.1 is 0.01, right? And if it's three, it's 0.1 times 0.1 times 0.1, and so on. So that's pretty reasonable, right? So let's say that I get into a situation where, I know the prevalence of the population is let's say something that's a little bit more prevalent. Let's say something like a coin flip. Probability of getting heads on a coin flip is 50%, right? So the probability of getting two heads in a row, since they're independent, coin doesn't know what it flipped before, is going to be 0.5 times 0.5, or 1 in 4, or 25%. If I flip it three times, right, then it's going to be 0.5 times 0.5 times 0.5. 1/2 times 1/2 times 1/2 is 1/8, which is 0.125. 12.5% of the time, you can get three heads in a row. Similarly, you get three tails in a row 12.5% of the times, right? 0.5, that's also 0.5 times 0.5 times 0.5. So that's pretty simple there, right? What gets complicated is that if we set a new condition where the probability of what's the probability of getting two heads in a row, two heads out of three tosses, right? Well, there's a lot of ways that can happen. Heads, tails, heads, 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 tails. So each one of those probabilities is the same. Coin doesn't know how it flipped. Similarly with diabetes, if I asked you what's the probability of getting 10 people in a row who have diabetes, point 0.1 times point 0.1 times point 0.1 times point 0.1 times point 0.1. But if I asked you instead, what's the probability of getting exactly 2 out of 10 people who have diabetes? There's many ways that that can happen. And each one of those ways is equally likely. So you have to calculate all those out. Right? You have to figure out how many different ways that could occur uh, that are equally probable. So now, looking at it from the point of independence, we're not gonna use a very complicated formula, which is available, which is based on the permutations of all the different ways you can have successes, the ways that you can get your heads or your diabetes patients over all the different other possibilities along with that, right? We're not gonna figure that. We're not going to use that. We're going to use a calculator of some kind, either Excel, an online calculator, or something like that, to speed up that calculation for us. And I'm going to give it a try in a second. But first, I want to point something out that is pretty interesting. Turns up on tests a lot, right? And it's also something that you can kind of use for a test to see if your sample is truly independent. Now, let's say that there's a 20% probability that people are going to get the flu this year. Now, I got a cold right now, so I'm sensitive to this, but if you want, I'm going to try and turn away when I cough so that I don't wind up. Well, fortunately, when we work online, I can't cough in your face, so that's one good thing, right? So let's say it's 20% probability that you're going to get that a random person's going to get the flu this year, right? So let's say that we follow. We want to sample at the end of the year. We're going to do a survey. We're going to ask people if they got the flu or not. And let's say we pick 3 people randomly at the end of the year and ask them if they got the flu. Well, the probability, if it's an independent sample and it's really random, probability would be 0.2 times 0.2 times 0.2, right? So that's going to be 0.2, 0.04 times 0.2 is 0.008, right? It's a little less than 1% that all 3 of them would get the flu this year, right? I hope I'm right on that. Let's do it. Why not? Let's pull the calculator up and just go ahead and do it. 0.2 times 0.2 times 0.2. Oops, I did something wrong there. 0.2 times 0.2 equals times 0.2 equals 0.08, 1%. Okay, so now let's think about that for a second. If I were to do this repeatedly, take this big population and say randomly select 3 people, probability that all 3 of them would have gotten the flu this year is 0.008, right? But that's not going to happen all the time. Some of the time, a lot of the time, I might get some other percentage of people that sample that of 3 people that I would get more than 0.08 or less than 0.08. In other words, sometimes I get 2 out of 3, sometimes I get 4 out, so on and so forth. So what's the probability if I do this repeatedly? I would expect that my chances of getting fewer or of not getting this result 8% of the time, right? The probability of not getting 8% of the time is gonna vary on each sample. It's gonna be a different result for each sample, but overall it should be 0.08. So if I take 1,000 samples of size 3, right? And I look at that and look at what percentage of the time did I get a result where all 3 of them had diabetes? Well, that should occur 0.008, 8/10 of 1% of the time, about 1% of the time, right? So if I find that could be 1,000, could be 10,000, I'm just illustrating a very large sample. Let's say that I find that in fact that the result was not 1% of the time that of these 10,000 times that I sampled 3 people, but actually 5% of the time that I got this result where all 3 of them had diabetes. Well, gee, What that tells me is that it's possible that this wasn't really an independent sample, or the result is not it wasn't really a random sample, or the result was not independent. In other words, maybe there was something in the way that I sampled people who knew each other, and if they know each other, they had physical contact, they might be more likely to get the flu, right? So a good test for seeing whether this is really independent random sample is to check with a large sample size whether or not you truly get an average of that percentage of the time getting the results you expect. Does that make sense to you? Did I explain that well enough to at least get by? I'll wait for a response. I know there's a little bit of a lag. Are you okay with that, Paul? Does that make sense to you? How about, oh, I noticed there's some more guys, some more people logged on now. How about you other guys can also respond if you want to. Okay, so that's kind of thing that, that goes a little bit beyond the simple question of the independent samples and probability. So that might come up. Well, how about now we deal with the other, let me go back to the chronology of what we've gone through. Can we do another example, see the percentage of people who do that? Okay. All right, let's say that um, 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 let's say 30% of the people in the population have the flu right now. It's really bad season. 30% of people have the flu or a cold right now, including myself, right? Not the flu, though, fortunately, so far. All right, 30% of the people have a cold. I randomly sample that population, right? I pick a random sample of two people from that population, right? Well, what percentage of the time would you expect to get both of those people having a cold at that moment? If you guys are just logging on, my graphics pen is not working right now, so I'm kind of scratching this out on my trackpad. What do you think that would be? Zero point 0.3 times zero point 0.3, right? Okay, why can we do that? Because it's number one, the result is independent. The result of the first test does not influence the result of the second. In other words, if the first person has flu or not, well then, since it's a random sample, the second person has the same likelihood of having a cold, right? So zero point 0.3 times zero point 0.3 is going to be 0.099% of the time, both people will have a cold. Well, now let's say I take repeated samples of size 2, right? Well, some of the time I'll get two people that have a cold, both of them have a cold. A lot of the time I'll have only one because only 30% likelihood, and a lot of the time I'll have none out of two people, and then maybe another two, maybe a lot of ones, maybe a lot of zeros, right, and so on and so forth. Well, on the average, if I averaged all of these, I would expect that I would get the expected result that if I sample two people in this population, 9% of the time I would get two people. So what percentage of the time do we get two people when we do this? Well, if it turns out to be 9% of the time, if you do this many, many, many times, the average result of if on the average the result um, two people comes up 9% of the time out of all of these trials that I've done, well, then that confirms for me that this was probably a random sample and the results of the first and second person are independent. If I get something different than 9%, like in other words, if I sample two people 1,000 times and I find that the amount of times that I got two people, excuse me, the amount of time that I got two people was 200 times out of 1,000. Well, 200 times out of 1,000 is 20% of the time, right? That would suggest to me that this is not true. That either these are not that these results, person one and person two, are not independent, or my sample was not truly random, right? So let's keep an eye on that in case it comes up, and it might come up in tests before. Let me move on a little bit to the chronology of the course a little bit. So some of the things that I think you should concentrate on. You should review data types. right? Because data types turn out to be pretty important in this course. I'm gonna go to a Word document or Excel or something like that so that you can read my chicken scratchings. Okay. Okay, so I would concentrate on, for instance, going review my data types, right? Because it's likely, since we covered that in the first session, we spent a bit of time on it, and it turns out it's more important than you would assume it to be, right? I would make sure I know my data types. For starters, that you understand the idea of categorical, or sometimes called nominal, right? Data, which is basically just names. For instance, a handedness, left-handed or right-handed, is categorical, right? It's a category. It's not something that relatively has a different value or anything like that. Hair color, city, state, and so on and so forth. Those are all nominal categorical. A few tricky ones, for instance. What do you think about the last four digits? Well, before I bring that up, let me bring up a second category here. Second category is numerical, right? Sometimes people call it numerical. Okay, sometimes people call that scalar. SPSS calls that scalar. So that's a number that's on a number scale, right? And another category is called ordinal. Ordinal is a kind of a form of a categorical nominal variable. It's a name, but the names have value relative to each other. Like, for instance, one could be interpreted as greater than the other, right? So, for instance, if we were talking about ambiance in a restaurant, and we said the ambiance was good, fair, or poor. Good, fair, or poor are the ambiance would be a ordinal variable, right? Because the values good, fair, poor, even though they're names, they have relative value. They have relative. You can kind of quantify them into relative values. Although you can't really say how much better fair is than good, how much better fair is than poor, or how much better good is than fair, and how much better excellent is than good. They don't really quantify like a number would be, where you could say, well, the difference between fair and good is 10 and 10 and so on and so forth. It's interpretive. And you can't really say whether the quantity or you can't quantify exactly whether or not the difference between good and excellent is the same as between poor and fair. Right? So, classic example of that is pain scale. Even though it's numerical 1 through 10, those are really those are not real measured numbers. They represent a person's interpretation. They're using a number instead of low pain, medium pain, high pain, right? So one to two is greater than one, but you can't really quantify if it's different than the difference between 7 and 8, for instance. And one person's two might be another person's four, right? And so on. So ordinal is kind of a special uh, uh, version of categorical, but it's different. It's handled differently in statistics. SPSS, these are basically three categories that SPSS uses, right? So you might see a few more turning up. For instance, where categorical, where numerical is concerned, you might see a version of that which is called discrete, right? And discrete, we're usually talking about a numerical variable, a number, but it's usually part of a count, right? Like when you count things, like for instance, siblings. How many siblings do you have? How many cups of tea have you had today? How many people were in the coffee room today, and so on and so forth, right? So that's discrete. It usually implies an integer, and it usually implies a relatively small number. Okay, so because it's part of a count. Now, SPSS really doesn't distinguish for that for most of the stuff that we're doing. They just consider it a numerical variable in SPSS. But in case it comes up and you need to interpret it, you have that. But let me ask you, most of these are pretty straightforward, but I noticed that one that a lot of people had an issue with. Last four digits of your social security number. What kind of variable is that? I'll wait for a response. I know there's for you guys that are watching this online, there's usually a little bit of a lag. What kind of variable is the last four digits of your social security number? I'll wait for some bold person out there to type it in. Think about who would ask that, right? What are they doing? What are they confirming when they ask you that, right? They're doing the same thing as when they ask you your name, right? They're confirming your identity, right? Who's that? It's you, right? That's actually a numeric. That's actually, excuse me, that's actually a categorical variable. That's your ID. That's your name. It's just ignore my spelling. It's actually a categorical variable, right? Because it's your ID. It's identifying you. In other words, that number. Let's say that number is 1234. That number 1234 does not actually have a value. Somebody else's number is 7349. Right? Those two numbers don't really have a different value. They just identify a different person. So it's just the same as a name. So that would be a categorical or nominal variable. Now, how about let's try another one. Let's say occupation. Okay, well, that's going to be a nominal variable also. So it's going to be name of your occupation. How about the number of cups of tea that you drank today? Right? Well, assuming that's going to be an integer, I would say that's a numerical variable, and you might call it discrete, right? How about the average number of cups of average your average number? Let's see. Let me try something else. How about your bowling average? Anybody bowl? Is that like old hat? Is that like am I giving away my age by talking about bowling? Bowling average. What would you call your bowling average? Right? That's a numerical variable, right? It's going to be an average. Okay. And how about blood pressure? Right? Is blood pressure 120 over 80? Is that discrete or is that numeric? Is that numerical? Can I also call that discrete? 120 over 80, right? I don't think so, right? Because blood pressure really is a number on a scale. Even though you might say your blood pressure is 80, right, for one measurement of blood pressure, even though you might say your blood pressure is 80, that could really, it's just simply a convenience to round that number up. It could really be 80.1 millimeters of mercury. So you have a little bit of interpretation. So yeah, review your data types and make sure you're comfortable with them to some degree. One of the next things that we did, we went over, we started talking about a little bit of probability and logic, and we talked about Venn diagrams. So when you look at Venn diagrams, one of the things we're interested in Venn diagrams is trying to understand what these probabilities are in terms of populations, when they overlap, when they don't overlap, and so on and so forth. So I'm drawing two populations here. One is A, that might be people that are left-handed, and B might be people who are, let's say, have A might be people left-handed, B might be people who have red hair, right? Okay, so in A, if I asked you the probability, what the probability of A would be, well, that would be represented by this entire area here, right? Now, there is some overlap here. There are some people that are both left-handed and have red hair. Those are those people that are in this area here. Okay, so the area that represents the probability of being left-handed is A. The area that represents the probability of being left-handed is A. The area that represents the probability of being having red hair is B. But this area here, people in here are both, right? So that's called the intersection. That's an upside down U. That's the intersection. people that satisfy this probability of A intersection B, in other words, A and B, and when you see that intersection, you can almost phrase it and, right? They represent this group in here. In order to satisfy this, you have to be both. So that's why this overlap is included here. Okay, so what about the probability that you have red hair or you're left-handed, right? Well, the probability that you have you're left-handed is A. Probability of A. Probability that you have red hair is B. Again, I apologize for the cold. If you want to include both of these probabilities, you would call that the union, and you can interpret union. This one as you can interpret intersection as being and, in other words, has to be both, right? And you can interpret union as being or, right? Either or of these will satisfy this. Probability of A, union probability of B is going to represent everybody in here because they're all either A and B, A or B, or A and B. So that both of those would be selected. We're going to went over a sample exam. Do we have access to the sample exam? The sample exam was posted for the class that's having the exam on Monday night. What class are you in? Which group are you in? What are you in, BIOS 610 or 11 or PH 750? For you other guys that are there, what happens is I principally am doing this for guys in BIOS 611 because they have an exam on Monday night, and they had some sample questions posted. And what I usually do is I post them to the other two courses so that if they want, they can drop in and use this as a review as well. Oh, okay. You should be able to see that. That I believe we posted that in session 4. Let me check that out. Hang on a second. Let me go there right now. Let me see where that got posted to. Oh, over here. Oh, look at that. It's turned off, I think. Let me see. Practice exams. Hang on a second. Let me see what's there. Ah, okay. Hang on a second. I'm going to fix that right now. Somehow it got turned off. You should be able to see that now. If you watch the video, I had it up on the video so you can go through it on the video. For you guys, as you get closer to exams, I'll be posting some examples for you guys as well. This one, you should be able to see this. You won't be able to see this. That's practice stuff for exam 2. Okay, we don't need to worry about it. Yeah, we're just worried about exam 1, one exam at a time over here. Okay, I hope that helps. Good. Okay. And so you other guys, don't worry about that as we get closer to exam time. For you guys that are strictly online, I mean, you're going to have more than, you're going to have a period of time, a range within which you'll have to take the test. It won't be at a specific time and hour. You'll be able to manipulate that a little bit, start on Monday instead of, you'll have a few days where you can decide, well, I'm ready to take the test now. But so we'll worry about that as we get closer to it. Okay, but yeah, for BIOS 611, this is a little bit more of a immediate issue. Okay, so yeah, you have those issues with the Venn diagrams. You should review that as well. Now, going back to the probability and this idea that we can have many different outcomes. One of the things that we examined was this idea of a dichotomous variable, variables that can have two values. They're very common. They're things like whether you have a disease or don't have a disease, whether you're left-handed or right-handed, and so on and so forth. So they come up quite a bit. So we have a special area. There's a special area of interest to us. Since we're talking about variables with two values, we call those dichotomous or binomial. Okay, those exhibit a special kind of relationship, a binomial relationship. It approximates. We can have binomial relationships that approximate a normal distribution, right? So, for instance, let's say with our diabetes example, let's say that we sample 10 people at random. I don't want to use diabetes. I want to use something. Well, let's say I'm looking at a population which has a high incidence of diabetes, maybe a nursing home, right? Nursing homes in New York City, right? So I'm going to say that the prevalence among nursing home patients in New York City of diabetes is 30%, 0.3, right? So I'm going to take a sample size, right, of 10. Sometimes we call that trials, right? Our trials is 10, right? And I'm concerned about, what's the probability, right, that the number of successes, the number of people that I pick, if I take a random sample of 10 people from nursing homes in New York City, what's the probability that within those 10 people, that sample that I take, that let's say that 3 of them are diabetic, right? Well, if I think about it this way, if 30% of the people are diabetic and I sample 10 people, the most likely outcome that I think I would get is 3 people. However, that's not going to happen all the time, right? If I randomly sample 10 people, maybe I'll get lucky and get 3 people, exactly what I expect. But a lot of times I'll get 2 people or I'll get 4 people out of the 10 because I'm randomly sampling. Even though it's 30%, I may get more than 30% in my little tiny sample of 10, right? So I know that it's clear that the most common outcome that I would get is going to be 30% because that's 10 people 30% of the time, then I would expect to get 3. But the other outcomes are going to happen, but less frequently. So, for instance, I would expect that that the next most likely outcome is going to be close to 30%. It's going to be either 2 or 4. And the next most likely outcome to those, but although much less frequent probably, is going to be getting 1 out of 10 or 5 out of 10. The further I get away from my most likely outcome, which is 30%, the less likely it's going to be to occur. For instance, the probability of getting all 10 people have diabetes, if I pick 10, must be really small, right? That would have to be really a long shot, right? That's like when you go to the casino and you keep seeing like the same number turn up all the time. Doesn't make sense, right? So that doesn't seem like very likely. However, I could get 0 out of 10 or 1 out of 10, depending on further away I'm from 3, the less likely that I'll get that particular outcome. Now, this is a binomial distribution. There's a formula we could use to calculate. Remember our formula tree. You could build a formula tree or use a formula to look at all the different equal possibilities and add them all together to see how often any particular outcome might occur. Two out of 10, 3 out of 10, just like we did with one head, 2 heads, 3 heads, and so on and so forth when we did our tree. So how am I going to do this? Well, the way I'm going to do this is I'm going to actually calculate. Okay, now notice I called the number of people that have diabetes successes. Kind of weird thing to call something about somebody who has a disease, right? But on the other hand, what I'm saying is that I found the result I was looking for, right? So I'm going to write down here. I'm going to write 1 through 10 here. These are all the different possibilities that I could get for the number of people that have diabetes out of a sample of 10 people. 3 is going to be the most common result. I know that already. Let's actually calculate what the probability is of getting exactly 3 people out of 10 that have diabetes. Equals binom dist. You can use not dist if you want to, or binom dist. Now, what's it ask for? It asks for the number of successes. The number of successes is 3. I'm going to put the 3 in there. Instead of putting the number 3 in, I'm going to put in B23, right, which is 3. Okay, comma, the number of trials, which is 10, comma, the probability of success on any individual pick, right? In other words, it's 30% on any individual person that I might pick, and cumulative. Now, cumulative, I'm going to say false, because I just want the probability for exactly 3 out of 10 people being diabetic. I'm going to hit enter. And the probability that I would get exactly this outcome if I randomly selected 10 people from this population is about 27%, right? So now I'm going to do it for 2 also. Equals binom dist. You can use either one of these, okay? And I'm going to use 2, comma, that's 2 is the number of successes. Trials is 10. Probability is 0.3, and cumulative is going to be false. Okay, and notice it's a little less likely than 26% is. And if I do it for 1, I'll just put 1 in this one, not even bother to do that. 1, comma, 10, comma, 0.3, comma, false. It's going to be a lower probability. And as I get further and further away, 0, comma, 10, comma, 0.3, comma, false, and close. So these are all the probability of getting these exact outcomes. Notice as I get further away from my most common result, that it gets less and less likely. Well, I can click in here. You can see the formula up here. The fact that I used the number to the left of this means that I can just click on the corner here and drag it down, and it will do each calculation for me. This will substitute 4 for the number, 5 for the number, 6 for the number, successes, 7. You'll still use 10, and so on and so forth. And now we'll be able to see all the probabilities. And take a look at it. When we get to 9 out of 10, it's really 1 in 10,000. And we get to 10 out of 10, it's very, very tiny likely we get 10 out of 10, right? But as we get closer to 3, we can can actually graph this, in fact, and you can see what it looks like on the table. I wonder if we can do that quickly. See if we can do this without messing this up and confusing everybody. There you go. Look at the probabilities here, right? It looks kind of like a normal distribution for you guys in some of the other classes, especially ones that missed a few classes. We haven't talked much about normal distribution yet, but for 611 we have started covered. See, it's almost like a normal distribution. In fact, there's a way we could simulate a normal distribution with a binomial distribution, okay? And we can approximate it using a normal distribution. Okay, so the other thing you might want to know is on the test is we might ask you something like, what's the probability of getting 3 or fewer people who are diabetic in a sample of 10? Well, 3 or fewer, this satisfies that criteria. This does, this does, this does. So if we wanted to know the total for that, we could just take the sum of all of these probabilities. And that's the probability of getting 3 or fewer, 3 out of 10, 2 out of 10, 1 out of 10, or 0 out of 10 in this population. Another way I could calculate that is to calculate it this way, equals binom dist, parentheses, and let's see, 3, comma, 10, comma, 0.3, right, number of successes, number of trials, 0.3 probability on the individual, and true for cumulative. And when I say true for cumulative, what's going to happen is that it's going to add up the probability for 3, 2, 1, or 0 together, and we'll get the same result as if we had just added those probabilities together. So if you're on the test, you have an extra time, and they ask you what's the probability of getting 3 or fewer, you could use this, binom dist, and then true for cumulative. And then if you have the time, you can go back and check it by, doing it for each individual outcome and adding them together. Okay, so sometimes these word problems can get a little bit tricky. For instance, what's the probability of at least 4 people have diabetes? Well, at least 4 people means 4 or more, 4, 5, 6, 7, or 8, includes 4, right? So literally, it doesn't include 3, 2, 1, and 0. So the probability of at least 4 people having diabetes is 1 minus the probability of 3 or fewer having diabetes. Oops, got to put an equal sign in there. Right? So you got to interpret the word problems. 35% of the probability of getting 4 or more people that have diabetes. Okay, are you guys okay with that? Does that make sense? I don't want to spill too much time on this. Are we comfortable with that? Okay, so the binomial distribution is likely to come up. Next thing that's likely to come up is what we've learned about the normal distribution. And I'm going to have to go back to my chicken scratching since my pen's not working right now. And pull up another sheet. And the first thing we learned about normal distribution is just a special kind of distribution that's based on probability when we take a sample from a population, And there's a lot of things that follow an approximately normal distribution. Maybe blood pressures, maybe blood sugar levels, and so on and so forth. And the idea with a normal distribution is that it's based on the fact that our sampling is random, and that the likelihoods of different values differing from the mean is it's just random. Okay, it's just based on probability and randomness of the sample. So let's say we have a normal distribution. Normal distribution, a few properties that we'll see in it is that really what I'm looking at here is the idea of a histogram. For instance, if I started to sample a population and I was measuring this population's blood pressure. So let's say that in this population, that the average blood pressure, notice I'm using mu for average, that's a population, right? Say the average blood pressure in this population is 100. Well, we would find a lot of people, even though the average is 100, there's going to be a lot of people that are going to be less than 100, a lot of people are going to be more than 100. In fact, the average implies about half of the people are going to be less than 100, half of the people are going to be more than 100. So if we took a sample, instead of looking at the population, if we took a sample and we took many people and measured their blood pressure, well, we would expect the most likely outcome is going to be about 100, say 90 to 110, say in there. And maybe between 80 and 90, we would see fewer people. And between 110 and 120, we would see fewer people. And between 70 and 80, we would see fewer people than that, right? And if this is a frequency distribution, a histogram, right, we would see it kind of step up like this, right? Might be fairly uh, 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 fairly mirror imaged here, fairly smooth. As we increase the sample size, we can narrow this so the individual bins, there are many more individual bins, and eventually, if we take the entire population, or if we look at this from the perspective of what this would look like mathematically, we get a nice smooth bell-shaped curve, right? And that bell-shaped curve is characteristic of a normal distribution. Okay, what other characteristics we have? Well, it's symmetrical about the mean. So the mean and the median are the same value, and in a perfect normal distribution, they're right in the middle there, right? And the distribution of the values for the population are evenly distributed between to the left of the mean and to the right of the mean. 50% of the people in the population are to the left, 50% of the people are to the right, perfect normal distribution, right? Well, there's some other properties that we understand about normal distributions, including the relationship between the mean and the standard deviation. Standard deviation is a measure of spread. We calculated it earlier in the semester. And so let's say standard deviation is equal to 10, right? Well, one of the properties we know about normal distributions is that standard deviation helps you to understand how spread out this population is, what the characteristics of this population are. So the standard deviation being equal to 10, well, what does that tell us? Well, the empirical rule tells us that in a normal distribution, right? Normal distribution, 68% of the values, roughly 68% of the values, are within one standard deviation below the mean. I'm going to put a -1 there, and one standard deviation above the mean. That represents 68% of the population. Another way to look at this is if you randomly select somebody from this population, there's a 68% chance they're going to be in this range between one standard deviation below and one above. Well, what is this? In this distribution, if the mean's 100, that means that 68% of the time you'd find people between 90, one standard deviation below, and 110. All right. Well, the empirical rule goes further. It tells us that 95% of the population is between two standard deviations below the mean and two standard deviations above the mean. Right? So we can then look at this and say to ourselves, well, the probability of picking an individual from this population that's between two standard deviations below the mean, two standard deviations above the mean is 95%. Right? So we can start to deduce certain things here. For instance, we can deduce that, well, since 95% of the people, this is going to be 80, right? Two standard deviations below, so standard deviation is 10, and 120. We can start to deduce that what percentage of people are going to be above 120 blood pressure, right? Well, let's think about this. 95% are between 80 and 120, right? So that leaves 5% of the people unaccounted for, right? Well, there's two areas that weren't accounted for here. The tail at this end and the tail at this end. So each one of those tails must represent 2.5% of the people. So if I ask you what percentage of people had blood pressures in this population over 120, you would say it's probably about 2.5%. Similarly, you could say what percentage of people had a blood pressure below 80, and you could also say about 22.5% be likely. The other thing you can say is what percentage of people had a blood pressure between 90 and 100? Well, since this is symmetrical, since 90 to 110 represents 68%, 90 to 100 must be half of that. So 68%, this would be 34%, right? That's between 90 and 100. What's the percentage of people that are below 90? Well, since this is 50%, everything to the left of the mean is 50%, right? Well, if this is 34, below 90, it's going to be what's left, or 16, roughly 16%. Well, that's great for situations where we happen to be lucky enough to be able to, number one, remember this is an estimate, not a perfect value, but this is also a convenience for us, but it's not exact. If we really want to know this, we need tables or calculators to calculate this for us. So I'm gonna go to that example. Maybe that example sheet. I'm gonna open that up. Let's see if we have an example of this in here. Oops, don't need that right now. Word is a little sluggish when it opens up. Well, let me click it away. It'll take a sec. There we go. I'm ready now. Good. Okay. Like I said, I'll post this with the other guys as we get closer to exam time. Numerical summaries, blah, blah, blah. Okay. Oh, yeah, let's just quick review here. The mean and the median and normal distribution are the same. If the mean and the median are not the same, that suggests there's something that's like an extreme value that's pulling the mean away from the middle value, the median. So for instance, a very low value or a very high value, right? The mean is not resistant the median is much more resistant to outliers, being affected by outliers, than the mean is. For instance, if you have a very high value, right, it's only going to shift the mean by one person, the median by one person, possibly, right, one value possibly, one subject possibly, but the mean can be dramatically affected by a very high value or a very low value that's averaged in. So the median is much more resistant to impacts from outliers, something that may come up. Okay, and you might want to go through, like interpreting these tables, for instance. In this table, count up the number of people. The height of the bar represents the frequency, the number of subjects, people, occurrences. 4, 8, 4, 8, this is 10, 14, and 3 is 17, and I don't know what that is. That looks like a 9, right? 26, 26 and 4. Well, actually, I think the problem might say, 50 individuals, 50 individuals here, right? Well, it's a probability that you would randomly select someone that weighs between less than 120 pounds. Well, it's going to be 8, 10. You're going to have 18 people out of 50 that weigh less than 150 pounds. So the probability is 8 over 50 or 16%, 0.16, right? Okay. Okay, that's the median and mean. I want to get to something that uses the Z table or Excel to calculate a probability. Okay. Probability. Okay, let's take a look at this one. On a psychomotor development index, I think I reviewed this. I'm going to make up my own sample because I reviewed this in the previous review session. So I'm going to make up a different one myself, just so we can attack it from a little bit. Sometimes when you vary this a little bit, suddenly a light goes off. Right. So let's say that I'm examining a population. By the way, one of the things you might want to remember is mu and x bar represent the mean. Mu represents the population mean. X bar represents a sample mean. Sigma represents the population standard deviation. SD, or S, frequently used, represents a sample rather than a population, a sample standard deviation. X bar approximates the population mean, and SD approximates the population standard deviation. But the only way you ever really know the population mean or population standard deviation if you measure it for the entire population, right? That doesn't happen very often, but we'll be getting into that later on as we move on in the semester. These are called, when you talk about mu and sigma, those are called parameters, right? I'm just going to put para up here. And X bar and SD are called statistics, okay, in case it comes up. So now let's take a look at a population, excuse me, a population that has a mean. Let me think about what I can sample here. Let's say I'm looking at blood lead levels in children in New York City schools. Okay, so the action level now is I think 0.05, 5 micrograms per deciliter of blood or something like that. Let's say we're looking in the suburb of Detroit, Flint, Michigan, where they had that issue with blood lead levels, and they randomly sampled, or they sampled all of the children in that area, so the entire population. Let's say mu is equal to the average blood lead level was 0.4. It was 4 micrograms per deciliter. 4, I'll make that a 4 rather than a 0.4. And the standard deviation was equal to, let's say, 1. And standard deviation is equal to 1 microgram per deciliter. Okay, keep the numbers fairly even. Okay, so now let's assume for a moment that the distribution of blood lead levels was normally distributed. Probably wasn't. There are probably people, young children at the far end of this. They got much higher doses and so on and so forth. Let's assume for our purposes that it's normally distributed. So the mean is in the middle, and 50% of the values, even though it doesn't quite look like that here, are below 4, and 50% of the values are above 4. If I use my empirical rule, right, I could say, let's say I'm going to draw 1 minus 1 standard deviation, which is the same thing as level of 3, and plus 1 standard deviation was the same thing as a level of 5 micrograms per deciliter, and this would be 6, and this would be 2, right? 95% of the children would have a value between 2 and 6. That would be our empirical rule. But let's say I need to know a little bit more about, let's say, I want to know what, let's say I think I mentioned that the action level for children with elevated blood lead levels is about 5 micrograms per deciliter of blood. What percentage of children in this population are below 5? How am I going to figure that out? If I use the empirical rule, since that happens to be exactly plus 1 standard deviation above the mean, I can use the empirical rule. The area to the left of the mean is 50%, right? So we know that's part of it. But then we also have this area between the mean and one standard deviation above. Well, we know between one standard deviation above and one standard deviation below, that's 68% of the population. This means that this area above the mean to 5 is 34%. So approximately 50% plus 34% or 84% of the children in this population are below the action level. What percentage of children are above the action level? Well, since 84% are below the action level, 16% must then be above the action level. In other words, from 5 micrograms per deciliter above and so on. So let's say that I want to do this more exactly, okay? And I want to really figure out what percentage are below and above, okay? So the way I would do that is I'd say to myself, okay, 5 deciliters, how many standard deviations above the mean is 5 micrograms per deciliter? Okay, well, I would figure out what the z-score is, or what the number of standard deviations that represents. So z is equal to the difference in the value, right? In other words, from the mean. So x, right, the value I'm interested in minus the mean, the difference between those two values, and divided by the standard deviation. So x minus the mean is going to be equal to, it's going to be equal to 5 minus 4, which is the mean, leaves 1, over the standard deviation was 1. So the z-score, as we already figured out, is equal to 1. Except this time, I am going to look up on my z table. I happen to use this one. You can use the one in the book. We've posted this, I think, a few times. On my z table, I'm going to go to the positive side, which is the side, which is the side to the right of the mean. So that we know the area below that's always going to be 150% because it's the right of the mean, right? It's already got 50% below there. Okay, so I'm going to look up a z-score of exactly 1. So the z-score of exactly 1 is 1.0, and then the next column would give me the third digit, which is 0. So the area to the left of that is 84.13%, 0.8413. So this is so this to the left of that is 0.8413. When I used the empirical rule, what did I say it was? I said it was 84%. Not quite as accurate, right? But in the same ballpark, right? 84.1. So what percentage of the children, what's the probability of picking an individual child who has a blood lead level above 5 micrograms per deciliter? Well, probability of picking a child that's a level below that is 84.8413. Probability of picking a child that's above that is going to be just the difference between 1 and that probability. In other words, 1 minus 0.8413, or 0.1587, looks like, right? A little less than 16%, right? Which was what we would have figured if we were using the empirical rule. Okay, so what's the probability of selecting a child who has a blood lead level that's less than, let's say less than 1.5, minus 1.5, right? What's the probability of picking a child who has blood level less than 1.5? Well, again, x minus mu is 1.5 minus 4, which is the average, over the standard deviation, which is 1. So that's minus 2.5 over 1. So it's equal to minus 2.5. It's a z-score of minus 2.5. Well, where is that? That's all the way over here. A z-score of minus 2.5 is all the way over here. So less than that, it's going to be that little part right there. Okay, so let's see what that z-score represents. Except this time, I'm going to use Excel to calculate it. So it's going to give me the same thing. I'm going to give it the z-score that I calculated, which is minus 2.5, and it's going to tell me the area to the left of that. Okay, so There's a number of different functions. There's on Blackboard, I think you guys remember I posted. Norm, 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 S dist, parentheses. If I put in a z-score, see it's asking for the z-score. If I put in the z-score minus 2.5, it'll return the area to the left of that. And it's a little less than 1%. It's 0.6 to 0.062. So the area that I'm concerned with there is 0.0062. Okay, so good. Up. Okay, so I think we had a little bit of an interruption on the internet there. Have you guys, are you guys still there? Okay, how much of that, how, were we offline for a little bit, for a few, couple of minutes? Or were you able to follow this whole thing as I was going through it? Okay, I'm going to back up a little bit to the point where I think we might have lost communication. Okay, and what I did was I'm gonna get a fresh sheet of paper down. I just want to finish up with this to make sure we got this straight. The last part that I was discussing, the last example I was discussing, was a blood lead levels and have you heard? In case you've heard this already, I'm just going to repeat that last part of this just to make sure we got it. Okay, I mentioned a population where the average blood lead level was the mean for the population was equal to 4 micrograms per deciliter, and the standard deviation was equal to 1. So my question was, what's the probability of a child in this population having a blood lead level between between say 1.5 micrograms per deciliter and 2.5. 2.5 micrograms per deciliter. Actually, no, excuse me, 1.5 and I think 5 micrograms per deciliter. That's what I had brought up before. Let's stick with the numbers that I went through in the first part. Okay, 1.5 and 5 micrograms per deciliter. Okay, well, the standard deviation, so as I said, the empirical rule would suggest 5 is just one standard deviation above 4, right? So if I use Z, which represents number standard deviation, Z is equal to X minus mu over sigma, right? That would be 5 minus 4, which is 1, over sigma, which is 1. So Z squared is equal to 1. So using the empirical rule, I could say that the probability of me selecting random selecting a child has a blood lead level below 5 is 84% of the time, right? How do I know that? Because one standard deviation below to one standard deviation above represents 68%, and between the mean and one standard deviation above, since this is symmetrical, will represent 34%. So 34% plus 50%, which is the area from the mean down, right, is going to be equal to 84%. If I use the z-score to calculate this, a z-score, and I'm going to, this time around, I'm going to use Excel. If I calculate the z value, the area represented by z value, excuse me, using Excel, it's going to be equal to norm s dist parentheses, and it's asking for the z-score now. So z-score is a +1, right? Because it's one standard deviation to the right. It's 84.13, so a little bit more precise than the standard deviation that I got from the empirical, from the value I got empirical rule. It's really 84.8413, or 84% of the time. I would expect to 1.13% of the time I would expect to get a randomly selected child that has a blood lead level below 5. Well, probability of getting blood lead level above 5 is going to be equal to 1 minus 0.8413, which is going to be equal to 0.1587. It looks like, right? A little under 16% of the time you get a child that has a blood lead level above 5. Okay, assuming this is normally distributed. Okay, well, my next question was, what's the probability of getting a blood lead level in a randomly selected child between 1.5 and 5? Well, I've already figured out what areas to the left of 5. Let's take a look at 1.5 now, a 1.5. Well, 1.5, right, minus 4, which is the average blood lead level, over 1, which is the standard deviation. Well, this is equal to 2.5, right? It's a minus 2.5, right? 1.5 minus 4 is going to be a minus 2.5 over 1. So the z-score for this value down here below a value of 1.5. The z-score for that is equal to, the z-score for that is 2.5, right? So I need to go to my table and look up the area of the curve that is represented by a z-score less than negative 2.5. So negative 2.50 is 0.0062. It's less than 1% of the time I would get that outcome. So this area represents 0.00, and I think it was 62, right? So if I want to know the area between these two, right, I would just take the area to the left of 5, which is 84.13, right? And that's the area we're concerned with. But we want to remove this part of it. So I just subtract that, subtract 0.0062 from this, and my result is going to be the area between these two values of 1.5 micrograms per deciliter to 5 micrograms per deciliter. Okay, so hopefully you're probably going to get some examples like that, I would think, on the exam. So some of them might ask you to use the empirical rule or give you data that you can use the empirical rule for. Some of them will ask you to use either the Z table, as we discussed, or you can use Excel to get the same values. On Blackboard, you'll find an Excel document that I put up either for session 3 or 4, where it actually gives you different parameters for your statistics in Excel. For instance, we could have used, instead of norm s-dist, parentheses, and put in a z-score to get a probability, right? We could have, let's see, norm s-dist, let's say, for a z-score of negative 2.5. This is the one we just did. Okay, that gives us an area of 0.0062 to the left of that z-score. Okay, so you could have also used another version of this, norm dist. Okay, and Excel will prompt you. It wants to know x, the mean, the standard deviation. Cumulative is always going to be true for this particular function. So x was a value of 1.5 micrograms, comma, the mean was 4, comma, the standard deviation was 1, comma, and cumulative is always going to be true because we're looking to the area to the left, the full area to the left, and it gives you the same value for that area. Okay, one last thing that might come up, and that is that if I asked you in the same distribution I just spoke about, if I can't get back to that, in the same distribution I asked you what, let's say I asked you what percent, what value, how many deciliters, how many micrograms per deciliters, what value is represented by what value, what number of micrograms per deciliter represent the point at which more than that level represents 10% of the children. In other words, I want to know what level of lead represents the value where 10% of the children are higher than that value. So this is really what I want to know. I want to know what that is, right? So what I do know is that the area to the left of that is going to be 10%, which means the area to the right of that is going to be 10%. The area to the left of that is going to be 90%, right? So I want to know, what is that value there, right? What value is that where I can say, well, you're in the top 10 percentile of children that have blood lead levels. We really have to keep an eye on you, right? What level is that? Well, we need to know what the z-score is that represents 90% to the left and 10% to the right. I'm going to go back to my table. And here on my table, I can actually kind of skim through my table and look for what value represents 90%. So let's see, 90%, 89 and 90.2 I see there. Which is the closest to 90%? Here we go, 89.97, that's closest to 90%. What is that z-score? that z-score is 1.28. Excuse me, I got that right? 1.28, right? So that's a z-score of 1.28. If I have a z-score of 1.28, right, then 90% of the value is going to be to the left of that, 10% of the values are going to be to the right of that. But what blood lead level does that represent? Well, you remember our formula there, that handy little formula, Z is equal to the unknown value, the value we're interested in, minus the mean over the standard deviation. We can actually substitute that Z, 1.28, in here. So now the only thing we don't know is going to be our value of X, because we know what the mean is. X minus mean is 4 over 1, right? So you can always cross multiply here, right? So it's going to be X minus 4 is equal to 1.28, right? So X is going to be equal to, move 4 over the other side, and it's going to be equal to 5.28. So children with a blood level of above 5.28 micrograms per deciliter are in the top 10% of this population. Okay, so it could get a little tricky and ask you to kind of look up that, use that table kind of in the reverse. So I think it's a good time to call it a day. And like I said, like I may have said, depending on what happened during that brief period that we lost the connection, or it would appear to me that we lost the connection, at least some of us lost connection. Um, if you have more questions, please post them to Blackboard, and I'll make sure that that I respond to them by the time of the test as best I can. And I prefer you put them to the discussions forum, because then we can all see them. All the other students can also benefit from them. And sometimes, if somebody else will post a question that you'll benefit from because you were reminded about it and stuff like that. Okay, so have a good rest of the day off today. And for you guys in 611, I'll see you. Assuming that I'm ambulatory tomorrow with this cold, I'll see you during the exam. And for the rest of you, I'll see you either on Tuesday or online. Take care, guys.